we'll jump to it. So yeah, so I was the lead artist on Shooty Skies Overdrive. And I'm going to be talking about some of the technical art solutions we used to improve the experience and quality while also staying performant, because we had to hit the mobile GPUs on the Quest, Oculus Quest VR device. So, what is Shooty Skies Overdrive? It is a frenetic arcade shoot 'em up full of colourful, retro, and inane characters. It's a VR successor to our mobile release, Shooty Skies, which came out in 2015 and was a fairly successful title for us back then. We thought it would be great to translate this into a room-scale bullet hell experience, and it was our first VR game and one of our more ambitious titles. I had several objectives as a lead artist that I wanted to achieve. We wanted to use our existing art styles and assets from the original Shooty Skies mobile game, and that was to the effect of to hopefully speed up production so we weren't recreating too much art and assets, and give us a solid foundation of art style, art direction, and techniques to work from, so we weren't trying to reinvent the wheel too much or spend a whole heap of time trying to redevelop content when we're already learning how to make a VR game. And to that note, I wanted to take what we originally had and increase the quality of graphics and meet and exceed the current quality standard on the Quest, and also enable it to deliver some high quality graphics on the PC VR, but I'll be talking about that less today. It's mostly going to be about what we did for the Quest. So the big thing about targeting the Quest platform for us is that it had to look good, but also run smoothly at 72 frames per second, which on a mobile tiled GPU was going to be pretty difficult. So we had an existing style. We had a simple but strong foundation from Shooty Skies Mobile, this beautiful, low detail, very colorful, blocky aesthetic. We were using really simple animations, and we were able to effectively bring all them across, a lot of mesh swapping and just simple things like translation, rotation, and scale. Nothing else, no rigging, nothing else in terms of animation that way. And we had basic tiled, scrolling backgrounds. And we had some really highly performant rendering techniques to make sure we ran on a lot of different mobile devices. So one problem with all that was that it was designed to be viewed from a set orthographic angle, and that was not really going to help us in VR when we suddenly moved into a full 360 VR environment. That being said, we did have all these lovely assets. These are examples of some of the original assets from Shooty Skies Mobile that we were going to bring directly over into the VR. They had some synergy between the worlds, so we had this heavy metal hell themed world with hell bats and skull based arcade machines, very, very Doom inspired, and we had some retro arcade worlds with our take on Pac-Man ghosts and the Joust characters, just for a bit of fun. And we thought that these worlds were interesting in Shooty Mobile and could work really well in Shooty Skies VR. So that was sort of the template that we were working with when we were looking at translating our original assets over. So bringing that into VR, the biggest thing to note was that we were going to have some new gameplay elements. So it wasn't just like I said, an orthographic top-down shoot 'em up where you're moving a plane side to side and dodging bullets. Dodging bullets was still the core mechanic in the game, but our biggest evolution to it was introducing a first-person camera, which drastically changed how we were going to have to deal with the environments and characters. We needed to basically create environments that were centered on an arena you can move around, and by able to hold the pilot in your hand as you navigated the bullet hell experience and all the enemies, you could essentially bring that character right up to your face and have a good look at it, as well as the enemies coming towards you could also get right up into your face. So we needed to make sure that our characters could be viewed from extremely close angles and look good from those extremely close angles. So when we look back at those environments that we had created for Shooty Mobile, we quickly realized that they were not going to work. They weren't going to support our gameplay, and certainly needed to be redesigned. So we needed to create specific environments that had an arena for the combat zone, and the surrounding background needed to envelop this arena on all sides. And I really wanted to make the player feel like they were in a set location rather than just sort of in a space or you know, in a themed environment. I wanted that environment to actually envelop them and make them feel they were in a certain location. And we'll get to looking at exactly how those locations took place a bit later on, rather than these just sort of tiled scrolling backgrounds with layers upon layers of buildings or rocks and skulls or mall outlets. But one problem we also had with these environmental assets is they were visually lacking compared to what I was seeing as the platform standard on the Quest. They were lacking a lot of fidelity and were certainly repetitive. We didn't have any real sense of fore, middle, or background. And being flat colored and block shapes, we lacked a lot of gradients and soft lighting. And by being performant on mobile, we'd completely remove shadows. And being based in the air, that was easy to do. We were never going to have to worry about casting shadows to the ground. So we certainly were lacking a few elements that would really make it pop and feel great in a VR experience. So to that end, what looks good in VR? This is a question a lot of developers answered in multiple different ways, and some have done it really successfully. Others, are still working hard at it. I think we're still working hard at it, but it's always a challenge. But when I first put on a headset, the most overwhelming sense I felt in VR was that sense of space. This totally immersive environment that's completely different to any other experience you have playing mobile or console. You're suddenly somewhere, and everything around you can see is this environment that you're in. So to me, utilizing that sense of space and that that atmosphere, that presence of being inside somewhere was critical to the experience. And for me, there was a few elements that I thought really made that sense of space come to life and made it really immersive. And the biggest one was having depth. We needed to provide a sense of distance and position to the objects around you, and height gives a sense of scale and awe. And we didn't have any depth with our current background assets. They were flat tiling little procedural generated structures, and we didn't really have any height either. When we started porting them, they were made to feel pretty flat in mobile so that we could skim across them. So while they might look tall in some of those earlier pictures, they're actually really quite squat. And I found that especially in games like Beat Saber and other experiences where they didn't aim for huge amounts of environmental assets, that what they were using effectively was a lot of soft and fading light and shadows. And those kind of elements really actually allude to the relationship between objects and space. And we didn't have any of those soft lightings or shadows either. So we were going to have to start thinking about ways to generate depth and height and soft lighting and shadows for our experience. So in our first environment, which was the retro world that we were bringing over, we started to solve some of these issues. I started using color a lot to help generate depth and mood and atmosphere to it. We started to introduce height by tearing up the buildings as they went back into the background, so you had that little bit of sense of awe. And by adding just a touch of fog also really helped with distinguishing between the fore, middle, and background layers. And also we started to work on basically how to make a distinction between our combat zone and arena in the environment, which was just basically cut a big empty area out in the middle of the environment and make it feel nice and open so that the player could feel like they had a good area to move in, but a visual distinction of where their boundary was going to be for the gameplay, obviously in a room scale environment. And we had people test this. It's quite interesting. You can set a room scale in VR as big as you want. So I think we had some people testing in an entire warehouse, and they could run through the environment and back again just for a bit of fun. But anyway, side note there. So I started exploring when I was prototyping this world, adding a lot more gradient tones and using a lot of complementary colors to really drive this mood of the atmosphere. And I did a lot of that work with shaders, which was going to be key for how I was going to approach my thinking for the rest of the art development in this game. The background is my absolute favorite element in the game, and is a fun little shader that I wrote for that too. But having this very stylistic design had a lot of benefits. We were able to, because it was a 3D virtual environment that we were putting the player in and themed to, you know, a retro computer game world, we could sort of escape or circumnavigate some of those other needs of, you know, we didn't need shadows because we were basically replicating, you know, our own stylized outrun wireframe environment. So there wasn't going to be shadows in that environment thematically. But as soon as we started looking at our other environments, so we had a mall environment, and we brought over that heavy metal hell world as well, they weren't rendering anywhere near as nicely. So we were still using a lot of our flat color techniques and flat lighting techniques here. And we started to run into a little bit of trouble. So we're finding that our flat perpendicular surfaces lacked a lot of definition and depth, especially when viewed from first person perspective angles. So if you look forward at a whole bunch of rocks and, and this image here up in the top right, you can sort of really start to lose the information on the rocks in the background. It just looks like all one ambiguous shape, and it's really hard to discern the height tiers, as you can see from the image above it, where the rocks are actually, you know, breaking up their structure and cascading it into smaller shapes as they go up. And we're also finding that the flat colors were really uninspiring and dull, and not having those gradient colors coming in from, not having the same level of gradient color that we're using in the first environment, weren't really generating the same mood and atmosphere that we wanted. And we also felt with the characters that we're bringing across that they were also flat and lack definition. The flat colors and lack of shadows weren't helping here. They, in VR, in our early tests, they felt cheap and didn't really have that sense of depth and weren't feeling like they were part of the space. We wanted our pilots and ships that you're holding in your hand to feel like little toys, and they lacked that sort of sense of realism to them. And our enemies also needed that little sense of realism that felt like they were right there to touch and in part of the immersive environment that you were in. So to that end, we had a few problems that we needed to solve, and it was time to start analyzing the best ways to solve it. For me, it was looking at, you know, how can we improve the quality of our environment and our characters? What solutions are out there for us to use? And, you know, I sort of settled on three main elements, and that was to add softer lighting to generate that style and mood and atmosphere, and have a lot more gradient colors coming in as opposed to our flat colors. We needed some sort of shadowing in the environments and our characters to add contrast, especially, and help define some of that depth and the relationship between the surfaces and objects that we had in our world. So those ambiguous shapes could actually start to take form, and the player could see and realize what we were actually trying to do with our blocks, our block world, especially when you couldn't see it from that top-down orthographic angle that would show every face so easily. And to that end, we also wanted to add just a little bit of PBR support, so that physical-based rendering, to enhance what our materials could do with shadows and lighting and how it would all blend together. But we had to keep a few things in mind because, again, we needed to target the Quest, and the Quest needs to run at 72 frames per second. And just considering our gameplay, which, as I stated, is very frenetic and full of life and color, we were always going to require a large variety and number of enemies, and especially bullets, on screen and in your field of view at any point in time. As you can see from our screenshot here, there is several different types of enemies, an entirely detailed background, you know, your main character, chip and pilot, a ton of different bullets and VFX all going on at once. So there's a lot of unique dynamic assets on screen, and we were going to have to work out ways to keep our material complexity low, and other ways to make sure we were optimizing efficiently, so we could, you know, make sure we were running at 72 frames per second. And VR rendering especially is expensive, so it was going to be quite the balancing act. Fortunately, Oculus provides a ton of great documentation in order to help you get your games to be performant on their device. These were the main ones that are pretty stock standard and everyone was going to do. So you really had to keep your game running between 150 and 175 draw calls per frame. And that's a little ambiguous because you can have a lot of really cheap draw calls and it's less of a worry. But if you have, some really heavy draw calls that are using a lot of fragmentation shader work, then it's going to be a problem as well. One thing that was certainly a locked element was the amount of triangles and vertices you need to be running on screen at any time. And we did struggle with this in points. They recommended using forward rendering, so I won't discuss anything different between forward and deferred rendering because absolutely inconsequential when we're basically forced down the forward rendering path. And they were recommending the anti-aliasing level to be 4 times MSAA. And you absolutely need anti-aliasing in VR, otherwise it looks like a dog's breakfast, basically, especially when you're using blocky style art. It really shows up when you don't have any anti-aliasing. Oculus also recommends using single pass stereo rendering, which is basically when what you see in your left and right eye images are packed into one really long, extra double wide texture. So we were going to do those no matter what. That was fine, but we did have to find some other solutions within their guidelines to help us get that quality improvement that we were after. And there are a couple of things that we found, and Oculus was strongly recommending not to use any sense of any use of real-time global illumination, excessive pixel lights, or shadows if you can avoid it. And we were like, well, that's great, because we don't use any of them anyway. We had a great pipeline coming from Shooty Mobile where we were already ignoring those elements. And this is basically what we ported across, which is our VERTEX lighting structure. So all our shapes, all our characters, assets, environment assets, what have you, were all exported from our 3D package with vertex colors rather than textures. So we would then multiply that by our own custom vertex shader lighting, which is basically your most simple kind of lighting calculation, but run in the vertex shader as opposed to the fragment shader, which is what you'd see in generally most applications. And this is great and really performant because if you've got a cube on screen and there's eight verts or whatever it is, you're only running that calculation 8 times rather than X amount of times, depending on how big that cube is on screen for every pixel that needs to be rendered. So this method meant that we did not need to introduce pixel lighting or shadows whatsoever, and disregarding pixel lights and shadows would give us a ton of room for improvement elsewhere. And again, we're still set in the air, so we didn't necessarily need to worry about casting shadows to the ground anyway. We weren't going to get much of a benefit from directly casting shadows. Another analysis we found that was really useful to our decision making was inside their draw call analysis documentation, and this really highlighted it was a documentation that highlighted all the different use cases for material swapping, texture swapping, mesh swapping, complex and simple materials, and their cost at rendering time. And the 2 big things that we pulled out of that were that textures weren't going to have too much of an overhead as long as we kept them within a limit of around about 2 or 3. And sampling cube maps on their mobile GPU was pretty much comparable to sampling a 2D texture. And in this image on the left, you can see sort of the bottom 2 lines on the graph are sort of showing the difference between having 5 textures on a simple shader and 1 texture on a simple shader. So 1 texture for the gray line, 5 for the O line, and then the 2 above that are complex shaders. So when we talk about complex shaders, we're talking about Unity's PBR lit shaders. And they're significantly more expensive, but we can attribute that to the additional logical operations that are occurring in the fragment shader. So given our blocky flat style, we wouldn't have to worry about normal or specular calculations. So we could start to explore some other elements of PBR, and we'll talk about that a little bit later. So with textures being the way to go, we started thinking about, well, right, how can we get textures into our game for lighting? And obviously the stock standard for that is baked light maps. And this came across a lot in our research for how people were developing for the Oculus Quest, and they were kept saying, do your lighting through light maps. All your static environment assets, light map them. So I'm like, great, that's going to be great, nice and easy. Baked lighting is far cheaper and can be very effective. And storing light data in a texture or a cube map to be looked up later is far more efficient than calculating it at runtime. And it was going to be a pretty good solution for our static environments. But what about our dynamic assets? So baked reflection probes we could also use to sample our scenes, and this would give us a lot of ambient light and color coming from the scene onto our characters and enemies and anything else on the screen that wasn't the environment that we wanted to add it to. And we could also bake some occlusion into our characters, and that would help to get a lot of that shadow detail and texture in for much needed contrast. So we were going to look at baking a lot of our lighting data in terms of environmental lighting and character lighting through these three methods. One problem was, though, is that our existing pipeline didn't support these methods at all. So the tools that we were using, our pipeline consisted of QUBICLE for our 3D assets, Photoshop for our sprites, which is mainly for VFX, and Illustrator for our UI, and then that all goes into Unity, and we did a ton of work in Unity as well with shaders and other things to really bring our art to life. But that's it. There are no other 3D tools were harmed in the making of this program. So what is QUBICLE? Not everybody knows. It's a 3D voxel editor that we used on Shooty Skies and worked on with Crossy Road as well. It's a bit like drawing 3D pixel art. It's very easy and fast to use, but it's not very powerful. As I said earlier, it exports in VERTEX color, or it exports a lookup texture like this image in the bottom left. So it's basically going for each vert in our vert that gets created in our mesh, assign me a color and the UV, and we'll look that up later. It doesn't have any UV unwrapping or texture baking tools. It doesn't have any ability to skin or rig your meshes either. And we hadn't at any point extended our pipeline from QUBICLE into other 3D packages before getting into Unity. So we had to extend our pipeline, and from my background, I'm pretty good with shaders, but I lacked a lot of experience with 3D pipelines. I'm not actually that good with Blender, and please don't ask me to UV unwrap ever. And I hadn't done any light mapping before, and I didn't really fully understand what PBR was, but I knew I wanted it. So it was time to learn and apply a variety of new concepts and techniques. And I actually think this is really important to mention, as it's it really indicates, especially for me, that you can overcome challenges and difficulties when you don't initially know the answer. There is definitely room to learn and grow within any industry and take those challenges on board and meet them. So for me, one of my main approaches was to let Unity do the work. Why not use another 3D package? Like I said, I lacked experience with other packages and certainly the scripting languages. I haven't written anything in Python for over a decade. Another issue would be that a lot of the modifications that we would be doing are done in isolation between QUBICLE and Unity, and it was going to add another link in our chain. And I wanted to keep the amount of new concepts that I was learning, and we were learning as a team, to a manageable level, especially because we hadn't done a VR game before, and there was going to be a ton of new stuff already that we had to learn and apply. But thankfully, Unity has some pretty powerful tools that we can use and can also be scripted to our exact specifications. It turns out Unity had a solution for each of our problems, and I have a pretty good experience with Unity and C# after working in this editor tool for the last 5-6 years. Another great thing was that by using Unity to run a lot of these tools, we had access to our existing code base, our paths, and our identifiers within our scripts. So the first thing we had to do was make some UVs, because we didn't have any UVs. So we used a specialized import process for our meshes, where we would import our mesh, and at the import during import, we would create a separate modified mesh file, and on that modified mesh file, we would run specific modifications to that new mesh that was being generated. It was a foundation for a lot of stuff that we were doing throughout the work on this project. Unity's UV generator, we could use that to create basic UVs as well as a light map UVs, so we could start to then have UVs that could look up these textures for our models. We also use this process for color conversion. The models we were pumping out of QUBICLE in VERTEX colors weren't linear corrected. They came out in the gamma color space, and we were using the linear color space, so we had to convert them. Then we also added the elements of animation baking here or there, as well as a variety of other little techniques, but they're not the main focus for today. So by doing this process, we now had UVs and light map UVs, and we could now light map our environments. So baking time. Light maps made a huge improvement to our virtual space. So if we look at our previous image of our hell world, everything's flat. It's really hard to get an idea for what the background's doing. The colors are basically blending together so flatly that it's hard to define shapes. But as soon as we started using light mapping, we had shadows, and they were creating that contrast and adding depth and definition between our objects. So, the stairs on our arena here are really showing each individual stair. Our rock surface at the background and all the cascading levels are starting to now having the ambient occlusion is now starting to define those shapes much more clearly, so we can see that relationship between our objects take shape, and the lighting was giving us much more tonality and more mood from the greater range of colors. So we were ticking that box for atmosphere and mood that we wanted. And now that we had light mapping in our pipeline, we started developing future environments with light mapping in mind. So this was our hub scene on the left, and our mall scene on the right, and we started to make use of multiple lighting sources and emissive materials to really add a lot more glow and light bleeding across surfaces to really enhance their mood and feel. And this was taking consideration from creating our models right through to setting up the scene and then baking. So you can see with the store lights in the mall how the green neon is just bleeding out onto the pavement, and this started to look absolutely fantastic in VR. And because it was all texture lookups, it was really cheap to run rather than relying on real-time lighting to achieve any of these effects. And to that note, we could then also use Unity's light mapper to bake our occlusion textures into our dynamic assets in a process known as prefab baking, which I found in my research in one of the Unity blogs, where they talked about how this team was calculating the lighting on their objects and storing it as a new texture and assigning it to a material's ambient occlusion parameter once it had all been done. So this was super effective for us, as it allowed us to ignore other 3D packages to get that to get the additional shadowing detail that we wanted without having to rely on any real-time or runtime shadows. This is also a really useful process because while for us it's really unique because we don't have UVs in our models as they're coming across. I imagine a lot of other people would generally be working with models that have UVs and have the capacity to be ambient, have ambient occlusion baked while they're developing them easily in 3ds Max or Blender. But if you start to think of this as a process that would work really well with procedurally or dynamically generated worlds, if you have a whole bunch of meshes that you generate but then fuse together into a single prefab, you can then you reuse those meshes in a variety of ways to create a variety of tiles or elements that you can then bake together in Unity and then save that data to be generated at runtime, either procedurally or dynamically. So there are some pretty cool applications for this kind of technique going forward if it suits what you need for your development and your project specifically. So it's good to think about things outside the box. So this was a tool that I spent a lot of time on writing and using. Basically had a separate prefab bake scene where we would designate which objects to bake. They would then be loaded in, spaced out so they didn't occlude on each other. And then we'd prepare the meshes again by regenerating any UVs that had been already mapped, so that we could then run the light bake. It would then create an inclusion texture, and then we would update the UVs in our mesh with the light map scale and offset. One thing that we found really handy with this was being able to plan for material complexity. So we could take we could bake multiple enemies into a single texture quite easily to reduce complexity. And being within Unity, we could look up, you know, our gameplay hierarchy for our class structure for our enemies. So we would have, you know, popcorn enemies or dive bomb enemies or arcade machine enemies. There'd be multiple varieties of these enemies within a single group. And knowing that within the gameplay, those groups would swarm at a single time and pull out the variety of assets that we had for those objects at the time, so that, you know, for every popcorn enemy type, we had 3 variations, and we would be spawning all 3 of those variations at once. We could make sure through this system and by looking up our identifiers that those elements would be baked together, so that at runtime we've got one material for all 3 enemies, that we're all sampling one Atlas ambient occlusion texture. And that allowed us to have less textures in our VRAM and less textures changing per frame as well, which we're going to help later on for optimization, and enabled us to do effective dynamic batching, which was critical for our enemies, given that they were going to be on screen a lot in large groups and numbers. So we ran the light mapper for our characters with just a basic ambient lighting setup, but it was important to note that we opted for really high samples and resolutions to compensate for the way meshes were composed from QUBICLE. So I know this is a terrible screenshot, I should have a better one, but where the buttons on a TV protruding from the panel face of the TV, it's drawing extra quads and extra vertices rather than just sitting on top of that. So that made the Unity's light map generator, UV generator, a bit fiddly to work with. So basically using these sorts of settings for our light mapping was really effective. And this was really difficult, I found, during the process of doing this, was trying to find adequate resourcing to actually tell me the best way to light map. It was really difficult to find resources out there. So I'll be putting these up later for people to look at if they're struggling with light mapping, to see exactly what worked for us. And from then, we would generate a new texture from our light map. So we would take the light map texture that exists in the scene and then copy it and save it to a new texture that we would then assign to our object's material. One thing we had to watch here was we had to monitor our light map resolution so that we would only be generating 1 light map per bake, because if we were trying to Atlas, you know, 3 models onto a single texture, if we had 2 light map textures, that system was suddenly broken. And because we were just concerned with shadowing, we were able to just use a single channel texture, given that we only had grayscale data. And then the final thing we did was just basically update the mesh with our new UV coordinates, the scale and offset. And our shaders would look these up later to sample that texture. So the results of our ambient occlusion baking was pretty subtle, but quite effective. It certainly provided that much needed contrast as well as tone. So you can start to see a little bit more shadow in the skull art and the skull's eyes, and a bit of blurred shadow as the skull sits on top of the coffin box, and shadowing in the creases and in intersections between the timber and the coffin and the handles at the back. And for our character here, the face is far more defined, but you're also starting to see a bit of color rather than just, you know, darkened, you know, rather than just being pure black being multiplied into there. We're starting to see brown come through on that skin tone rather than just a darker, blacker version, which is really nice. But it just needed a little bit more. And this is where we started to look at using environmental reflections in conjunction with our ambient occlusion. So as I spoke about earlier, cube maps were pretty cheap way to sample textures as well. Just as cheap as 2D textures. So being able to bake our environmental reflection probes in our newly wonderfully lit scenes, we could get beautiful lighting data that we could then look up at any time on our characters to create all that soft bleeding light that would bleed over the faces and make them feel far more interesting and feel part of the environment, and add to that environmental immersion that I really wanted to achieve. So we'd get like I said, a wider gamut of soft gradient lighting, really help put our characters inside the world. Thankfully, we did not have to write a large and complex scripting tool to generate and assign environmental reflections. It comes pretty standard in Unity. So this is just a little video. I wonder if I can full screen it from here. Just showing some of the results we had, and you can really see how that environmental light is dancing on our assets as with their basic animations. It was really nice at making those characters pop, especially off the vibrant and detailed backgrounds. You still needed, as far as gameplay was concerned, to be able to see your characters and see what you needed to be shooting or see what you needed to be avoiding. And with how vibrant and colorful and detailed our backgrounds were, being able to make sure that our enemies were popping off that with a bit of light reflection really helped as well. So we were really happy with these results in the end. Does this go back out of full screen? Oh dear, we're stuck. There we are. Awesome. Oh, all the way out. Too many escapes. Sorry, 1 second. They should bring us back to where we were. Yeah. So also on some of these characters, we're starting to see some of the PBI elements that we enabled on characters, and they really also attributed to helping to feel part of the environment that they were in. And yeah, the ambient occlusion was really adding that soft contrast and tone, and really being able to see all the faces and the relationship between our block surfaces as they intersected with each other. And to achieve all this, in the end, the other thing that we needed was to write a little shader support. So we'll jump into a little bit about what we were doing with shaders in our project. So we opted to use Unity's URP pipeline. It came with optimized shaders and graphics that were VR ready, which was super handy. And the scriptable render features allowed for some additional flexibility that we're going to make use of here or there. Unity's URP shaders natively support our new features. They handle the lit material handles occlusion, environmental reflections, and light mapping. So check. And they range from simple to complex. And like I said, all that PBR support is embedded in their libraries. But there was a little bit of a lack of support. URP does not support our existing features. They don't natively support vertex colors in the shaders that they give you, and they don't necessarily support the same way we were doing vertex lighting. So we would need to integrate those features as well as some other features to support our gameplay. Another problem is that URP shaders were written with HLSL rather than CG programs. So it's a similar language and a similar syntax, but one big problem was they had completely different built-in helper functions and variables, and all of that lacked documentation. So all the functions and methods that I was familiar with were now completely different, or in some cases unsupported. And I love this quote. Somebody had been asking what's involved in porting, existing materials and shaders into HLSL in Unity's URP, and what they say is that what the internet doesn't tell you is that writing a shader is easy, but integrating with an engine, and especially lighting, is hard. And we certainly experienced that. So for me, in order to understand what we needed and what was going on with all the URP shaders, was to basically take a deep dive into their library and perform a biopsy on it. So I spent hours stepping through each shader and the shader includes in their library, looking up all the new predefined variables and helper functions, and basically stepping through the entire flow of their lit shader from their main path to their inputs to their vert and fragment shaders, and right into how they're accessing and using all the PBR functions, so that we could get an understanding for what we needed, what was too expensive, and where we could input our own functions. So we ended up writing our own library that was modeled off these shader structure, but tailored it specifically to our needs. So we replicated basically a lot of the include structure you would look at when you're looking at, if you download Unity's built-in shader folders, and it has, the shaders and then the includes and all the little functions and variables that exist in all those includes. We started to replicate that and use them where we needed to. We excluded lots of operations or rewrote them to increase our runtime performance. We also wrote a lot of our own custom includes for easy access to functions that were specific to us, and this included all of our VERTEX lighting, anything that we're doing specifically with VERTEX shaders to maximize performance. We had Mighty Functions include that had support for Fresnel and other VFX stuff that we were doing specific to our game. And so that made it easier for me when I was writing a new shader for a new asset. I could easily state, okay, this is the library I'm using, and I just need to write this function and send what parameters I need, rather than rewriting everything for every individual shader. That was super useful. So these are just a few examples of some of the shaders we wrote. So our Mighty VERTEX lighting has structures for lights, how that light structure is initialized, and then the basic lighting calculations, some interpolations on that lighting, and the global shader parameters that we were using to write it all. So all of that is all bundled into one library file, and when I'm writing my VERTEX shader, all I need to do is call this one function and send through the parameters that I needed, and I'd get my lighting back. And that was really easy to replicate and really clean and easy to look at in the end. So yeah, having all your custom predefined variable structures and initializations and operations live in shader libraries is a really easy way to keep your project structure nice and clean and easy to access. When we came to looking at accessing PBR operations, we also set up a lot of our own PBR parameters into an include, which was where we were sampling our occlusion textures, as well as all your standard things like specular and metallic. We're able to get rid of a lot of stuff that we didn't need, like I said earlier, like normal maps and anything that was running too heavily on the fragment shader. And we could afford a lot of the new logical operations in the PBR, like your specular calculations and your reflective calculations, simply because we'd done away with pixel lighting and shadow calculations. We had that overhead was there and available in our fragment shader to do those other advanced logical operations. So that was one way we were able to include a lot of that additional PBR rendering capabilities. So again, that was really handy. And one other thing to state there is we basically still accessed a lot of the Unity's core shader libraries. We just sort of create an input above. We basically we did away with their top layer structures. We'd create a shader. We'd write our pragmas out, and which vert function and which fragment function to call. We would have our own shader structure for all the inputs and all the parameter declarations. And then we'd write what was happening in the VERTEX and the fragment shader, and then we'd write what was happening that we needed to happen on a PBR level, and then we'd let all those additional functions from our PBR functions that we were writing, so cascade down into the additional shader libraries. Like I didn't need to write, what do we got here? Like their reflect function. I didn't need to rewrite that. I just needed to access it, and then we needed to find the right way and the right place to access it. So we wrote, a ton of includes and a ton of shader libraries to basically rewrite the top layer of what Unity was doing. There were some constraints and mistakes that we had to keep in mind, and some issues that I did. one thing to note, especially, is that functions and variables have to be compiled before they can be accessed in a shader. So this is why you'll often see your shader library includes at the top of a script. So your structure then becomes really important. And one of the mistakes I made, especially here in this little function nugget, is don't have common functions residing with specific functions. So this function here was in our vertex lighting shader, and I ended up accessing how we interpolated brightness and saturation in a lot of materials that didn't use vertex lighting, but because they were accessing the vertex lighting library, they still needed to declare the parameters specific to that vertex lighting library so that it could compile the whole shader. And it just kind of got messy and difficult in the end. And another issue here with this function is that I am directly accessing material parameters of brightness and saturation. What you really should do here is pass through those variables when you're calling the function. Otherwise, those parameters have to be declared on every single shader that you are using to access this library. And again, it just muddles it and makes it a little less flexible and difficult to use. And finally, I'm just going to have a little bit of a quick talk about some of the optimization techniques that we use, because I'm starting to run a bit out of time here. Luckily, there's only a few things here. So I'm not going to go into full detail in terms of what instancing and batching is. I'm just going to have a quick chat about some of the specific things we did. We wanted to enable GPU instancing as much as possible, because that was going to be critical for us to hit 72 frames per second. We wanted to use dynamic batching as much as possible on our characters on screen, the enemies and our bullets. Didn't matter so much for our pilot, because we're only ever going to have one of them on screen at a time. And this was and we did this to reduce draw calls as much as possible. So one thing that we did specifically was split up our enemy characters to better support our batching methods, which was to split our enemies into bases and then separate out the animating parts, or as well as any parts that could be the base could also then be duplicated across multiple enemies if the enemy was set up correctly. So in this way, we're only ever animating the elements that would change over time and over frames. So these meshes are the only ones that are swapping. But this base here for our YouTube enemies stayed in the buffer constantly while these enemies were on screen, rather than swapping, and could be instanced effectively for each 3 variations of this enemy. So each pair of screens here is one enemy, and our background monitor would instance effectively for all 3 variations of our enemy on screen at once. Some other solutions that we had to keep in mind or use were forcing a lot of our light mapping to be indexed into specific light maps. So that way we could try to bundle our assets in front of the camera into the same light map textures so that they could better statically batch, because it's difficult to have, you can't really have 2 elements batching together when they have a different light map. Unity will prevent that from happening. So we were able to get our entire stage here in Hell all batched into the one light map by forcing all of our mesh renderer properties onto, forcing the mesh renderer property to use a single light map texture. And that was super handy to allow for better static batching. We also had to reduce our vert count quite significantly, and we did this by culling the back and bottom faces of objects where we could, but also by baking the extents and boundaries of our elements, of our environments, into skyboxes. So all the buildings at the back of the mall are actually baked into a skybox using Unity's environmental reflection probes as well to generate those cube maps, and that was really handy. In summary, I think ultimately we met all of our objectives. We migrated our existing art style and those performance techniques that we established, and we improved on the quality of them dramatically, and we absolutely hit 73 frames per second on the Quest. And we've also hit 90 frames per second on the Quest 2, which is super cool, and we should be releasing an update for that soon. And we did this by using technical art and the lens of technical art to look for and provide solutions to enhance those capabilities. We were able to bridge the gap between quality and performance and we targeted the improvements that would give us the most impact with the least overhead. And hopefully this has highlighted why our choices and solutions were important for also delivering our VR experience. Like, we were able to generate that sense of space and atmosphere in our environment, so that when you put the headset on and loaded into our game, you absolutely felt transported and felt like you were in this, fantastic, vibrant, colorful, interesting world full of inane characters. And that immersion was there. And when you picked up your pilot and you looked at it, it had that just additional element of rendering that made it feel a little bit more real. So thank you. Hopefully we still have time for QA. I kind of pushed that a little bit longer than I thought I would.
Thank you very much. We've still got a bit of time. So first of all, fantastic talk. You annoyed the channel because all the original questions that were asked at the beginning, you managed to answer as you went through the talk. But as soon
that's good. That's perfect.
Exactly. As soon as you started talking about shaders, however, everyone perked up again. But we do have a few questions.
Yep, go for it.
Lewis first asks, any particular problems or challenges you had running using particles in this whole pipeline?
Oh, sure. Yeah, I was going to talk about that, but I ran out of time when I was writing my talk. So, yeah, our particles, as you know, Lewis, I have a tendency to go overboard with particles, and we had to keep that in mind. The biggest issue there was just too much transparency and overdraw, and especially using linear color space, it's recalculating that linear correction far too much when you're using transparency. So one thing we did was we created hexagon meshes for all of our glows to put the glow textures and sprites on for our VFX, so that it wasn't all that alpha that's in the corners on a square texture was being ignored, so we could gain a little less overhead there and try to use opaque particles as much as possible where we could. So a lot of the explosions are using more opaque rendering than transparent rendering.
Cool.
Other than that, those were the main ones that we used there, because I don't think there was too much else with the particles. Those were the two main ones. Yep.
Andrew asks if when you moved to the bake lighting pipeline chain in your system, how did it affect your level iteration time and creation process?
Terribly. It was terribly slow. I didn't know light mapping. It took me a long time to understand how to set up the parameters for light mapping effectively. And if I go back to that screen, I don't know how to get back. Come on, there we are. Yeah, you've got your actual light mapping parameters in the lighting window, but then you also have what do they call it? Sorry, 1 second. I'm terrible with remembering terms all the time. Yeah, you also have specific light map parameters as well. So it was trying to spend a lot of time trying to find the correct balance between your scene lighting parameters and your light map mode parameters as well. And then from there, it was also just a case of learning how setting up lights in your scene would work effectively. And obviously, when you make a mistake and you run a 10-hour bake on trying to get a final render look nice, you then have to plan to bake that again. So it was a matter of setting things up during the day and running bakes at night. So I had two computers on the go at home, one that I was working on constantly and one that was constantly baking either environments or our characters over and over again until we got the results that we wanted. So yeah, there was a lot of iteration there, but most of that was generally due to not knowing how to do it and trying to learn how to do it. It was just a thing that just cost iteration more than anything else.
When you're talking about the Unity's URP, you brought some memories back from me as well. I've definitely had projects we've been dabbling in, using it, not using it, figuring out how we should get into it. And you talking about the lack of support was, I think, everyone's biggest problem at the moment with it. Have you found the support getting better since? And I know they've changed a lot in the last year, but have you seen a lot more support since you started doing this project?
I've seen it come in drips and drabs. but then again, I've also stopped looking to the same extent because I found solutions. Recently, I've been trying to write our own scriptable render class for Bloom, so we can try to get that working on the Quest 2. It's actually pretty close, but it's kind of just neat for me. But I've had to basically grab assets that exist on the store that are doing Bloom in the URP and completely dismantle them as well to find out how they're working and exactly how to write a custom script, a custom scriptable render pass, because Unity doesn't tell you anywhere in their documentation. They say look up these projects, and they have the the Sobel outline project, and that was kind of helpful, but that's also on a different URP platform than what we're currently at. So the entire structure of that's changed as well. So yeah, I think it's still lacking a lot, but I think most of that's because they're still trying to develop it, and once they have a consistent way forward, they can then start to write documentation. I mean, I didn't mention it in the talk, but we started off doing everything in the lightweight render pipeline, because we did that 2 years ago before URP became the standard. So it was even more confusing then because things were either specifically referencing the lightweight render pipeline, which was then no longer supported, or the URP render pipeline. So yeah, I still think there's a lot of room for improvement there.
Oh yeah, I think we're out of time.
One last point, especially if you still go to Unity's documentation now and look up a shader function, and it's the CG program built-in helper function, not the bloody HLSL one. So yeah, that still annoys me.
Yeah, I feel that so much. I've been down that path myself. But we are out of time. Thank you so much. It was a great talk.